Good morning, everyone. My name is Zhixiong from MSRA, and I'm very happy to present our paper, 3L-Cache, Low Overhead Process Learning-Based Eviction Policy for Caches. This work is a joint work between Beijing University of Technology and Microsoft Research. So let's get started. First, let's revisit what is a cache system. Actually, when user has a request, it first goes through to the near edge closer cache system. If this got a hit, the cache responds the request directly without visiting the original server. It's not only accelerate the response times for users, but also significantly reduce the network traffic for the network operators. However, the cache space is limited compared with the tons of the data on the internet. The cache eviction policy is critical here to determine which data should be removed from the storage, the cache storage when the space is full. So there are two key metrics. The first one is the object miss ratio, and the second one is the byte miss ratio to reflect the response speed to requests and reduce the network traffic respectively. Both metrics are very important in evaluating the eviction policies. Over time, people have come up with various ways to improve the cache eviction policies. Looking at the recent trend, we found that the learning-based policy have gained a lot more attention than the traditional heuristic approaches over the past 5 years. The main reason for the shift, that is, the learning-based method can adapt to different workload and fine-tuning the parameters, which helps lower the miss ratio compared to the heuristic-based method. This is why, in this work, we focus on learning-based eviction policies. In the community, we classify learning-based eviction policy into 3 categories based on their learning granularity. The first one, that is policy-level learning, use RL to select among expert strategies, such as between LRU or LFU. The second one, that is the group-level learning. We predict the eviction weights of groups and eviction objects based on the group-level eviction weights. And the last one, that is object-level learning. We sample the multiple objects and predict individual eviction weights to make the eviction decisions. We evaluate the performance of these 3 categories by selecting the representative policies from each. In the figure, it shows that the missing ratio reduction from LRU, the higher the better. Our finding, that is, the policy level and the group level approaches can exhibit worse miss ratios in certain cases, but the object level learning performs well on the 2 miss ratios, and they are still very stable. But there is a very big downside, that is, the object learning comes with highest computation cost. Let's take LRB as an example. Its computation cost can be 172 times higher than LRU. On the top of that, we analyze the real-time CPU overhead using a Twitter dataset of HLB and HLB. We saw a huge fluctuations. The CPU usage could be swing anywhere from 1.5 times to 3 times. So given these observations and analysis, we want to ask ourselves a question: can we significantly reduce the CPU overhead of object learning while maintaining the miss ratio advantage? If so, it will become an ideal learning-based eviction policy. We first analyze the computation overhead of the objective learning policies. Actually, our conclusion, that is, the training and the prediction both dominate the computation overhead, but they shift, the impact are shift with the size cache size, with the different cache sizes. In small cache sizes, The higher miss ratio make prediction 83% of the overhead. In large cache sizes, prediction dropped to 45%, while the training remains steady and it becomes the main overhead. This highlights the need to reduce both training and the prediction cost for efficiency. Let's go into the details. We found both the CPU waste from the training and the prediction for sure. Firstly, reducing the training frequency from 2 to power 3 and 2 to power minus 3 cuts overhead by a half with no big impact on miss ratio. And for the prediction, we found the eviction ratio is relatively low, causing large CPU overhead. The LRB has 1.56 eviction ratio. The HLP improved that to 25%, but is also very small. This insight reveals the key challenge and our solutions for our further optimization. So we summarize our key challenges here. The first one, that is how to reduce the overhead waste in the training without reducing the model accuracy. The second one, that is how to reduce the prediction overhead without sacrificing the miss ratios. And last one, that is how to improve the generalizability across the traces. In the figure, you can see actually in our world, we need low overhead, low byte miss ratio, and a low object miss ratio policy. So we call our solution 3L-Cache. So this is a design overview of our 3L-Cache. First, to achieve the low frequency without harming the miss ratios, we introduce our train data collection mechanism. And second, we design our more efficient sampling and eviction method. Third, we develop a very efficient parameter auto-tuning mechanism, which efficiently adjusts parameters on the fly to enhance the overall system performance. So let's dip into the details step by step. First, our training data collection should filter unnecessary cache requests, reducing the training frequency while ensuring the high prediction accuracy. So we have a sliding window adjustment. We use a scaling factor. This is a hyperparameter, the sliding window to dynamically adjust the window size rapidly. And in the efficient sampling and the labeling, we have 4 steps. In the sampling, we randomly sample 1 object per request. And in the reordering, in the recording, we store the sample time, and we deny the duplicate recording until it re-requested. This is one of the key of our design. And in the labeling, we mark the re-request objects and record the interval. And in the updating, we retrain the model after accumulating M samples. In our experiment, we found the M should be between 32K and 122K. This approach ensures efficient and lightweight training. We use GBL to predict the log of next arrival time interval for an object. The reason we choose GBM is because it's effectively handles the missing historical features without requiring expensive imputation. And the 3L-Cache uses 6 input features to predict future arrivals. The experimental results shows they are sufficient to maintain the high model accuracy. Our second key design is the bidirectional sampling policy, which improves the eviction efficiency by prioritizing non-popular objects, reducing the prediction overhead. In an LRU cache queue, the popular and unpopular objects mixed, but non-popular ones tend to be accumulated at the tail. We leverage this distribution with 2 sampling strategies. First one is we sample it from the tail. We sample all objects in the last X% of the queue, and the remaining objects are sampled only if their access frequency is less than or equal to f. The second one, that is, we sample from the hat. This is because the newly arrived objects follow the ZFF distribution, meaning that most of them actually are non-popular. Since new and the hit objects mix at the hat, we use a record queue to track the new arrivals for faster identification and sampling. This continues until newly objects occupy less than Q% of the cache. By combining the two approaches, we optimize the eviction decision by sampling unpopular objects. So further enhance the efficiency and the eviction accuracy, we introduce accumulated prediction result for objects that were not evicted. This increased the number of the eviction candidates, leading to more precise eviction decisions. However, the accumulated precision results can grow into millions. Hence, we also propose an efficient management method to handle the large-scale accumulated data efficiently by combining the heap and the hash table. With these optimizations, we successfully increased our eviction ratio to 50, significantly reduced the precision overhead, while also maintaining high eviction precision. To achieve the generalization to different traces of our hyperparameter, we also design a parameter auto-tuning in 3L-Cache. But there are two details in the table, so if you are interested, maybe you can refer the paper. For the eviction, in the evaluation, actually we use 8 open source datasets covering more than 4K traces to evaluate the performance of the performance. We use 12 cache eviction policies. Actually, 6 of them are heuristic-based policy, and 6 of them are learning-based policy. For the best byte miss ratio, in summary, in small cache sizes, the 3L-Cache achieved the lowest miss ratio in around 30% of the all traces, as we present in the previous page. And in the Tencent CBS small cache size, we reduce the RLU, compared with RLU, we reduce the miss ratio by an average of 12%. And for the large cache sizes, actually, we can also find some benefit as shown in the figure. And for the object miss ratio, for the small cache sizes, the 3L-Cache cache achieved lowest miss ratio in 66% of all data traces we tested. The 3L-Cache reduced RLU object miss ratio by more than 14.8% at the 90th percentile, with an average of 23% in Tencent small cache sizes evaluation. We have a very detailed evaluation in the paper. Please check them if you are interested. And for the CPU overhead, which is our main goal of this paper, the mean CPU overhead of 3L-Cache is only 2.6 higher than LHD and 6.4 higher than RLU on average in small data sizes. In large data sizes, when compared with RLU, the mean CPU overhead of 3L-Caches is only 3.4 times. So I think this is all of our 3L-Cache presentation. I think in summary, actually, 3L-Cache has the low overhead online training design and the low overhead eviction design. It achieves a low overhead cache misses and a low object cache misses, a low byte cache misses, and it outperforms the state-of-art evictions in a lot of scenarios. So if you have If you want to check the code, please visit our GitHub repo. And thank you. This is all my presentation. Any questions?